The era of running isolated analog coax lines to a grainy monitor is dead. Modern physical security relies on highly converged, enterprise-grade IP networking. Today's integrated systems push high-resolution CCTV, access control, intrusion detection, and under-vehicle scanners across a single unified backbone. The core engineering challenge is forcing hundreds of disparate edge devices to communicate flawlessly in real time without creating massive network bottlenecks or overdrawing available power. Solving this requires a methodical, professional site survey framework, a strict set of validation protocols designed to build and verify the architecture from the ground up. This validation follows a strict 4-layer cascade. It starts at Layer 1, the physical edge. Data moves through Layer 2, the transport layer, carrying packets inward to Layer 3, storage and compute. Finally, everything is governed by Layer 4, software integration. Skipping a single variable in this cascade, whether it's a structural mounting limitation or an overlapping IP address, will invariably trigger a catastrophic network bottleneck or complete system failure. Theoretical hardware specifications are meaningless if they conflict with the physical realities of the deployment site. Localized lighting conditions must be verified day and night. If ambient light is insufficient, infrared illumination has absolute maximum distance limits that cannot be pushed through software. Before a single cable is pulled, you must validate structural feasibility, calculating the load capacities of mounting walls and the specific concrete foundation requirements for camera masts. Environmental exposure dictates hardware selection. Expected weather severity and localized vandalism risks require non-negotiable ingress protection and impact kinetics ratings. A camera's required resolution and field of view must be mathematically mapped to its intended analytic goal. Capturing a license plate requires specific pixel density. A wide-angle 2-megapixel sensor simply will not capture the required data. Complex security nodes like under-vehicle scanners or volumetric intrusion sensors follow these exact same physical deployment rules. If physical edge parameters fail to support the required analytics, the edge device captures compromised data. No back-end software processing can extract a clean image from a physical capture that lacks the necessary pixel density. Once the physical edge is validated, the focus shifts inward to the transport layer. Copper and fiber pathways form the circulatory system of the architecture. Designing this infrastructure requires calculating exact cable routing paths, identifying where armored conduit is necessary, and mapping junction box locations within strict distance tolerances. You must calculate the exact power over Ethernet loads. Every IP controller and analytic camera draws specific cumulative wattage that cannot exceed the switch's total power budget. Next is data capacity. Each edge node requires a baseline network bandwidth allocation, calculated in megabits per second. When you introduce heavy, continuous data streams like license plate recognition or UVSS, that aggregate bandwidth requirement drastically expands. High-volume data transport introduces a secondary engineering requirement, security. An open physical security network represents a major entry point for unauthorized access. Strict VLAN segmentation is imperative. CCTV, access control, and intrusion data must be entirely isolated from standard enterprise network traffic. An undercalculated transport layer results in IP hardware starving for power, or network switches dropping vital video frames, precisely when a critical security event maximizes the load. The raw data ultimately reaches the control room, ingested by network video recorders and compute servers. This head-end environment operates under strict physical constraints. Surveyors must validate available rack U space, ensure ambient cooling can handle the thermal output, and calculate the exact duration of the UPS battery backup. Sizing the system storage requires calculating a multivariable formula, camera bit rate, total note count, and time, yielding the total requirement in terabytes. Selecting specific video compression codecs, like H.264 versus H.265+, dictates the baseline bitrate of every camera on the network. That baseline then multiplies against the recording schedule, whether continuous or motion-triggered, and the legally mandated retention periods, which often span 30 to 90 days. Because hard drives will inevitably fail under 24/7 read-write stress, this massive dataset mandates redundant RAID 5 or RAID 6 configurations for failover protection. Failing to calculate exact storage needs or establish RAID redundancy turns a multi-million-dollar surveillance grid into a massive legal liability during a post-incident evidentiary audit. The final layer is the video management system, the vital intelligence engine that aggregates and governs the hardware. To function, edge devices require strict ONVIF compliance or native API integration. Without this, the cameras cannot execute commands from the VMS platform. Disparate hardware layers must execute digital handshakes with the VMS. An access-denied ping at a peripheral door reader is instantly routed to a centralized event log. This integration allows for automated workflows. A perimeter breach alarm can instantly command a PTZ camera to slew to the exact coordinates of the triggered sensor. Designing this layer requires deliberate compute check, deciding whether to process video analytics locally inside the camera hardware at the edge or centrally on heavy-duty servers. The sleek dashboard of a VMS provides an illusion of total control, but it relies entirely on the successful validation of the physical, transport, and compute layers beneath it. When executed correctly, this 4-layer architecture processes massive, complex, encrypted data loads without latency or unexpected interruption. Designing physical security cannot be done piecemeal. It operates as an interconnected ecosystem of mathematical dependencies. A client's requirement for facial analytics directly dictates the requisite compute power and terabytes of storage. That total storage requirement dictates the aggregate megabit bandwidth load forced through the network transport layer, and those specific bandwidth and power parameters dictate the final physical mounting location, cable run length, and IP rating of the edge device itself. Standardizing this methodology through strict surveyor checklists and formal client sign-offs is the only effective way to lock the scope of works and guarantee system performance. Relying on rigorous first principles validation is what separates a vulnerable collection of disjointed hardware from a truly resilient converged security architecture.